There's some association with power.
This week,
Like that.
we're gonna get my.
Say a couple things about the next homework. The first problem, we're gonna let G be a group and let X and Y be any two elements of G. Like we say the commutator of X and Y, which is sometimes written in the square bracket notation, is just X inverse Y inverse XY. And we define the commutator subgroup of G to be everything that's made up of words if the letters are commutators, right? So it's everything that you can make putting together commutators together, right? Sort of like our alphabet and our words. Number A, show that two elements X and Y commute, so XY equals YX, if and only if the commutator is one. So the commutator is sort of a measure of whether or not these two things commute. Show that the set of all commutators, just the set of all commutators, is closed under inverses and conjugation. What do I mean by that? I mean, show that if XY is a commutator and G is an element of G, show that the inverse of the commutator XY is still a commutator, and show that this conjugate, G inverse XYG, these are still both commutators. Number C, show that G prime is a normal subgroup of G. We defined normal last time. Remember, you also have to explain to me why it's a subgroup as well. And D, this is the important thing about commutators. Show that if N is a normal subgroup of G, then G mod N is abelian if and only if N contains the commutator. So this is it's an abelian quotient if and only if N contains the commutator. You don't know what this is yet, but I'm going to tell you today. Number two, suppose that G is a group and H is a subgroup such that the index of G and H is 2. That basically what that means that H is half of what G is. So if you have G as a set of N things, then the subgroup H occupies exactly half of that. I want to be more precise about that in a moment. Show that H is normal in G. So if you have a subgroup that's half the group, it has to be a normal subgroup. Is the same true if the subgroup is a third of G? Prove it or give a counterexample. And the next problem, we explore some properties of normal subgroups, examples. Show that if N is a normal subgroup of G and H is any subgroup of G, then the intersection of N and H is a normal subgroup of H. And number B, is it true that if K is a normal subgroup of H and H is a normal subgroup of G, is K a normal subgroup of G? It'll certainly be a subgroup of G, but will it still be normal? Prove this or give counterexample. And the final question is, suppose you have a group G, center ZG, that remember this is the set of everything, that commutes with everything in the group. It's at least the identity. Show that G is abelian if and only if G mod the center of G, which again I'll define today, is cyclic. Okay, any questions on that so far? So let us. Okay. So let me remind you, we have the notion of a normal subgroup. So let's recall last time. N is normal in G. Means these two sets are the same for every element of G. An equivalent way of thinking of this, G inverse in G still lives in N. For all G, and N. So it's a normal subgroup if every conjugate of everything in there is still in that group. Well, the last thing we defined was this notion of a left coset. let me, remind you of that. I'm gonna almost exclusively talk about left cosets, but there's a similar notation, right? What is a left coset of H and G? It is a subset of G of form GH. Some fixed G and G. Let me give you a couple silly examples, and then I'll do a couple of examples that got a little more teeth to it. Let's let a left coset this is G, H, H and H. Well, in this case, there's only the identity in here, right? So there's only one element. So in this case, it's just G. So this coset here would just be the element G, right? On the other hand, so kind of another extreme example is what if H is the entire group G, then the left coset is all of G, right? So those are two silly examples. Let me give you one that's got like a little meat on it. Let's let in this case, let's let H let's look at this subgroup here. And I wanna find all the left cosets. H in S3. By the way, let me make the parenthetical remark here that I could define a right coset, and I think a right coset would be what you think. The lowercase g goes on the right instead of the left, right? And it's the same sort of. So, well, let's go to the list, shall we? There, just multiply by on the left side the identity every time, and I should get this back. What about this? And this becomes two. There's another left coset. Okay, so far. Look at this one right here. Notice a key fact here is 2, 3 is actually in this. Right, agreed? So this is a subgroup, this is an element of the subgroup. I should get this back. And I do, just in the other order. Agreed. So this is 1, 2, 3. And this should be 2. And 2 goes to 1. 3 should do itself, and it does. And finally, okay. This should be 1, 3, 2 by 1, 3. You might want to make any observations about these cosets?
Subgroups unless they're being multiplied by something with an age.
Oh, that's a great observation. Did y'all get that? None of these are subgroups except for this one. Only if you multiply it by an element of the group. So notice when I multiply by E in this group, this coset's actually a subgroup. When I multiply by 2, 3, this coset's a subgroup. That's great, right? You might explain why that has to be true. If you have one of these if you have one of these cosets, the only way that this is going to be a subgroup is G is already in the group page. Yeah, what?
Whenever you multiply any element of a subgroup, you know you're multiplying one of those elements being E, which just gives whatever you're multiplying.
Right.
So you have to have either a matching pair or something to cancel out E.
Well, let's key on the identity, right? If you have one of these cosets, being a subgroup, it has to contain the identity, right? Now, it's not gonna, you're gonna multiply the identity by whatever G is, right? So unless it's the identity in the first place, it's gonna, so to get the identity back, you need G inverse in there, which meant that if G inverse is in H, then G is in H, so it already had to be in there. Okay, that's actually a great observation. The only way that this thing is actually a subgroup, the other cosets, these are just subsets. None of them contain the identity except for the one where we multiplied elements of the group. What else? Yeah.
The coset is only equal to the original set when G is an element of H. Makes sense? Am I saying that
Yeah,
right?
that's correct.
Okay.
And what else? These cosets actually form a partition of the original group, don't they? Right? In fact, let me kind of highlight the ones that are different. You've got this, and this one's different, and this one's different. Notice everything else is a repeater, right? This is a repeater, this is a repeater, and this is a repeater. So actually what we have is we have a partition in the original group because the original elements are here They all have to be in one of these. Right? All of them are in here. E 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. They all have to be in there. And there's no overlap. The intersection, there's nothing that's in more than one coset. Yes.
This could be a little bit of a dumb question, but I'm kind of confused about how you're getting the multiplied answer on the right side.
Oh, that's just, so it's function composition, right? So like this one, so let's start at 1. 1 goes nowhere, goes to 2. And then 2 goes to 3 and back to 1. And for good measure, 3 goes to itself. Other questions? So this actually, it looks like it forms a partition because everything in the group has to be in one coset. And let me prove that for you really quick. Take your favorite element of G. I don't care what it is. It's in the coset GH, right? Because the identity is in H. And when you multiply G by that identity, it'll be in there, right? For example, 1, 2, 3, it shows up incidentally here, but it also showed up when I multiplied by 1, 2, 3 because it has to be here. And this one happened to pick up the other 1, 2, right? So let's do one more collection of cosets. Let me do a different subgroup. I'm gonna do cosets with respect to a different subgroup. This time let's do N E 1, 2, 3. Now, let's look at E N. This is E 1, 2, 3, 1, 3, 2. Let's look at 1, 2 N. This is equal to 1, 2, 1, 2, 1, 2, 3, and 1, 2, 1, 3, 2, which is equal to 1, 2. Let's see what happens here. 1 goes to 2, back to 1, so 1's left alone. So let's start with 2. 2 goes to 3, and 3 goes to 1, back to 2. Okay, good. This should probably be 1, 3. 1 goes to 3. 3 goes to 2 and back to 1, and 2 goes to itself. Actually, these are the only 2 cosets because I've already got the partition. In fact, give me another element of S3 that's not E or 1, 2. Well, if I pick 1, 2, 3 in, right? That should get back the same group because I'm going to go 1, 2, 3, 1, 3, 2 identity, right? But any other of these, let's say 2, 3, you know, I guarantee you it will produce this coset. 2, 3, 2, 3, 1, 2, 3, and 2, 3, 1, 3, 2. This is 2, 3. 1 goes to 2 to 3. 3 goes to 1, and 2 goes to itself. And 1 goes to 2, 2 goes to 1, 3 goes to itself. So notice we get the same coset, just in a different one. Yes.
I already said this. In both these examples, the like H and N are subgroups, right? Does this partition happen if set we're talking about is not a subgroup?
I know we only want it to be subgroups
We only want it
here.
to be subgroups,
right?
okay.
That's, I mean, this is mathematics. I would not say that's not a fruitful path, but it's
I
one that
gotcha.
we're not gonna go down right
Okay.
now. Okay. So let me point out that I didn't look at let me also do something else. The order of the group was 6, right? Because it was S3. Agreed? Notice these 6 elements are divided up into 3 cosets, all of order 2. Agreed? And this, with this group, the subgroup's of order three. This has two cosets both of order three. 2 times 3 is 6. This is not a coincidence. So let me make solve your theorem. Let H be a subgroup of G. Let H be a subgroup of G. The collection of left, respectively right, cosets of H and G forms a partition of G. So the set of left cosets forms a partition, the set of right cosets as well. So in other words, G is equal to the union of GH and if GIH equals GJH, or I'm sorry, if their intersection is not empty, then the cosets are the same. So before I prove this, I'm going to give you a little definition, a little remark here. The number of left or right cosets of H and G is called the index. Of H and G. And it's written oftentimes this way. This is the number of left cosets of the group H and G. If G is a finite group, then the index is always finite. However, yes,
Is the index when looking at left cosets and right cosets always the same?
it's a great question. And the answer is yes. And we'll prove a theorem pretty soon that shows that. Yes, the number of left cosets, number of right cosets, that index will always be the same. So for example, the index of E12 equal to 3. And we saw this example, the index in S3 of E123, 132 is equal to 2. There were 2 cosets in this case. But even if this group is infinite, you can have a finite index, for example. Here. Now, I'm going to circle the elements of 2Z 2z is just the even integers, right? How many left cosets do we have? Actually, in this case, left coset, right coset, it doesn't matter, right? Because here my operation's addition, it doesn't matter if I'm adding on left or right, you get the same animal. There's 2z. Now, somebody give me an element of the integers that's not even. 5. Let's look at this coset. Notice this is just like 5 times 2z, except my operation here is addition, so I'm gonna add 5 to everything. If I add 5 to -6, I get -1, 1, 3, 5, 7, 9, 11, 7. Would everybody agree that this is all of the odd integers? Every odd integer is one of these, right? Because this goes forever in both directions, right? These are the two cosets because they partition it, right? Because every integer, it's either even, in which case it's red, or it's odd, in which case it's black. And there's no overlap, right? There's nothing that's both even and odd, right? Notice this coset is the same thing as 1 plus 2z. This coset, the even ones, is the same thing as -6 plus 2z. And in this case, how many left cosets do I have? Just 2, that's right. Red and black. You can generalize this example to instead of 2z, just take nz. You'll find the index is n. Let's prove this theorem. Any questions for you? We'll get to proving this thing. Yes.
Is there a way to find out what the index is gonna be? Like how many left
You
cosets?
bet, right? Not yet, but I'm gonna give you some nuclear weapons later and we'll be able to do that kind of, yeah, at least in some cases. Okay, let's see, need for partition. This one I think is gonna be the easy part. Since H is a subgroup of G and G is in G, H, GH and G is a subset of all G and G. Therefore, animals of this form are a subset of this, so the union is a subset of G. Right, sure. On the other hand, so let's push this a little further here. Also, if G is in G, then as the identity of G is in H, because remember, H is not just a subset, it's a subgroup, yes.
The first part, how can you prove that GH, never mind, subset, not subgroup?
Subset, right. And the fact that the union is a subgroup, we'll get from the next bit, because actually I want to show that union is all of G. Right? So if G is in G, then since the identity is in H, G times EG is in GH. So G is an element of GH, no matter what. And hence, G is contained in union of GH. So there's the first bit of our partition. We know that G, when you put all the puzzles together, you get all of G. Let me also point out, I should have mentioned this earlier, but of course, any one of these GHs is non-empty because any one of these GHs has to contain at least the element G. Little g. Okay, so far? Now, here's the partition part. We've got that when you put everything together, you get all of G. Now you need to show that if you got two different puzzle pieces, then either they're exactly the same puzzle piece or there's no overlap, right? So suppose XH equals, well, okay, let me take two puzzle pieces. I'm tired of writing these subscripted GI, so let me just call it X and Y. So suppose that XH and YH have something in common. The intersection is not empty. My goal is I want to show that these two things have to be exactly the same. So what does this mean? Well, Z lives here. So and Z also lives here. If I agree with that. Well, okay, so what does this mean? Well, setting these two Z's equal, X H1 equals Y H2. Okay, so doesn't this mean that X Y H2 H1 inverse? Everybody agree with that? So I want to use this. I'll start here. I'll use it. So let's let XH be any element of XH1, right? Then XH equals Y H2 H1 inverse H. And I don't know much, but I know that this is in H, right? This tail of H's is in H. Everybody agree with that? So this is in YH. Because this XH element is Y times something else in H. And what have I proved here? I proved that the coset XH is contained in YH. But the reverse is also true because instead of solving for X, I could have solved for Y and done the same thing, right? By symmetry of the proof. Everybody okay with that? So XH is contained in YH, but my choice of X and Y, of course, there's nothing special about them. I could reverse the process and got this. Y. And so left cosets partition. Any questions on that? We'll take this a little bit farther as well. This is actually very important in its own right. You're going to use this a lot. So, okay, two cosets, either two left cosets are either miss each other completely or they're exactly the same, correct? So you might ask yourself this, how can I tell when two cosets are equal, right? Because they're either equal or they're completely different. So is there a good way to tell when they are in fact equal? And we will answer that question presently. Proposition. Let H and G be a subgroup and X, Y, and G. You will find this useful in a number of contexts in the future. Then XH equals YH if and only if X if and only if X inverse Y. So this is the way to tell. By the way, this X and this Y, they're called coset representatives sometimes, right? Notice that with our cosets, it's the thing that you multiply by. Notice that this isn't unique, right? With our earlier examples, we usually had several coset representatives, right? For example, in the first example, you could have multiplied the subgroup E and 2, 3 by either E or 2, 3. So you'd have two different coset representatives. How can you tell when these two cosets are the same? It's if the inverse of this times this is NH. Let's suppose that XH okay, let's see if we can get a reasonable interpretation of this to help us move forward. Notice that well, since notice that Y is in YH, of course, because H has the identity. Subgroup there is very important. There exists H in H such that XH is equal to Y. Right? Since Y is in this thing and these two are equal, Y has to be in here. What does it mean for Y to be in here? Y is X times H for some H. Now multiply on the left by X inverse. And so X inverse Y is this H that looks an H. Okay, so far. How about the other direction? Suppose well, basically I can just reverse engineer what I already did, right? This means H in H such that X inverse Y is equal to H. Now multiply on the left by X, and I get so Y is XH. So Y lives in XH, and it's also in YH, right? Because Y is already in YH. Therefore, because we showed that there's one thing in the overlap, these two have to be the same by our previous result. Okay. Any questions on it? Okay, so here's a big one here. And this will actually be useful on, I think it's problem 2 on the next homework set. Might help you. Proposition 415. Let N be a subgroup of G. Then N is normal in G. If and only if Gn equals Ng for all G and G. So this is a big one because what this says is a subgroup is normal if and only if every left coset is actually a right coset, right? So this left coset corresponds exactly with this right coset, right? Now, I'm going to be a little sloppy here. You can sloppily think about multiplying G, little g on the G inverse up there on the right and get G and G inverse equals N, which is our condition for normality. But I want to be a little bit more careful with that and not work so sloppily with the sets. But intuitively, that should kind of remind you. This is a big thing. And the fact that left cosets or right cosets will allow us to use this to define a new kind of group. We'll see in a moment. Suppose first that N is normal and consider the left coset Gn. Of course, what we want to do is show Gn is equal to Ng. Since N is normal in G, give G inverse. The normality of the subgroup means that when I conjugate, when I multiply N, when I flank it by G and its inverse, I should get something else in N. And so that's the death knell right there, because this implies that Gn is equal to N1 G. Multiplying this equation on the right by G. Right. Therefore, what we've shown is anything, if I start with anything Gn, then I can rewrite it as something as a different N perhaps times G. So that shows it's contained here by symmetry. So again, like with our last argument, it didn't matter that I started with the left or the right. Ng is contained in Gn. So we get the same either way. On the other hand, suppose that every left coset is also a right coset, and see if we can prove that we have a normal subgroup. So So suppose for all G and G. Now suppose for all G and G. Gn is equal to Ng. That is, every left coset is also a right coset. Now consider for shorthand, I'll call this X. I want to show that, of course, X is actually an element of N. At this point, the only thing I know is it's just some other element of G. So since Gn equals Ng, we can write Gn as equal to N1 G1. Oh, no, actually G for some N1. Because this element is in the left coset in G, it also has to be in the right coset so this is in the left coset, this is in the left coset Gn, so it's also in the right coset in G. So I can rewrite that way. So let's look at X here. G in G inverse, which I've now replaced as N1 G inverse, which is N1, which is in N. Therefore, G in G inverse is in N, draw N and N, and G and G. So N is normal at G. So that gets you both directions here. Yes.
Can you explain more, what's the difference between N and N1?
N1 is just some different element, perhaps, of N. So this Gn right here lives inside this coset, right? So it's one of the elements in here. Since it's in here, it also has to be in here, which means that I can rewrite this guy that lives in here as a guy that lives here, right? And all I know about this N1 is it's some other, perhaps, element of N. It might be the same N here, but maybe not. Does that clear it up?
And does it work the same way on the other side too?
Yes. Yes. Okay. Is that okay? Yeah. Other questions? Okay, so I can do this more generally. If H is a subgroup of G, we denote the set of left cosets well, actually, you know what? I am going to go normal here because I don't want to confuse the notation. If N is normal in G, we denote the set of left cosets. And of course, I put left in parentheses here because left, right doesn't make a difference by G mod N. And this is just the set of left cosets. Here is a huge theorem. And this is a way to build new groups from old. And in fact, it's a generalization of, for example, how many of you have had a class we played with modular arithmetic. How many of you are interested in computer science or coding? This is a generalization of what's important in modular arithmetic and that sort of thing here. So here is the theorem, which I will leave you with and we'll talk about next time. Theorem. Here, 1.11. Let N be a normal subgroup of G. Normality, very important. Then a set of cosets of N in G, right in, forms a group. Actually, this collection of cosets itself forms a group. So now I've got a way to multiply these sets. Well, how do you suppose we do this? I gotta tell you how to operate it. Okay, so this is a big moral I tell in math stories. Math is complicated, and this is why you guys are all special, because you all are majoring in something that confuses and bedazzles a lot of people. But at the core of it, you should always try to do what's the easiest thing in the world. Now, I'm trying to make this into a group. What am I doing? I've got to find a way to multiply two cosets. Here's one coset, here's another coset. I've got to make this barf out a new coset. What's the easiest thing to remember that I can multiply these two and get a new coset? What should I put in the blank?
XY.
XY. Let's do it. This operation here, this coset times this coset, multiply the elements, new coset, that actually makes a group. You need it to be normal though. The first thing that you would need to do, in proving this, what's the first thing that we might need to do? So we'll cogitate this next time, but the first question is this operation even well defined? Right? I might take Xn for this representative and Yn for this. You might have a different one. Remember how the cosets have different elements in them? You might take X1 and Y1. So I would get XYn and you would get X1, Y1 in. We need to convince ourselves that you get the same answer every time. Those two turn out to be the same. Otherwise, this is crap, right? And we don't want crap. All right. Any questions? The math club today is very good. It's about mathematical game of set, something maybe play to interested in, and all you need is an set. So be there if you're interested, and I'll see you on Monday.